Just now we have raised many different examples including cube and necklace. Actually, we will realize if the target is different, corresponding permutation will be different too. Sometimes those could be several rotations over the flat surface. Sometimes we will handle the object in 2D, 3D space. Then we will be thinking over a flat surface. Actually, sometimes it can be tiled over a 2-dimension space, and this time we just need to consider the rotation. If we said if it was over the 3-dimension space, flipping is permitted. There is a special example, for example, a chessboard. If we take a look at the chessboard over its opposite side, if it was flipped around, can it be used as a chessboard still? Therefore, we must always consider whether it is a single-sided or double-sided. Under common circumstances, we will consider it cannot be flipped. For a cube, it can be rotated, it can have symmetry axis. Another type, which is more special for numbers, we can also use several permutations. Even the permutation on points, there are many different categories. Now we still take a cube as the example. For a regular hexahedron, just now we have said to study its permutation group. First, we may need to know the structure. How many faces are there, how many edges, and how many points? For regular hexahedron, 6 faces, 8 vertices, 12 edges. We can consider the permutation of its vertices, or the permutation of its faces, or the permutation of its edges. We first take the permutation of vertices as an example. For 8 vertices, we label them respectively 1, 2, 3, 4 until 8. We will see under different rotation situation what kind of permutations are there. The first rotation will be 0 degree because it contains total of 8 different corners. Therefore, there are 8 one-order cycles. There is only one of this kind of permutation. For face center to face center, it can be rotated positive or negative 90 degree. For now, for vertices, the rotation between the top 4 vertices, the rotation between the bottom 4 vertices. Therefore, there are 2 4-order cycles. How many this kind of different permutations are there? Because it contains 3 pair of different face centers, 2 angles. Therefore, it can generate 6 this kind of face center to face center permutations. If face center to face center rotated off 180 degree, at this point we realize the top 4 vertices perform 2x2 exchange, bottom 4 also perform exchanging. Because their exchanging contains 4 in total, there are 3 pair of face centers. Based on this kind of situation, we can take a look at the middle point of the edges. What kind of situation will it be? Similarly, the upper and the lower vertices perform 180 degree of rotation. Naturally, it will be 2x2 exchanging. Therefore, there are a total of 8 vertices. A group of contains 2. In total, there are 4 groups for 2-order cycles. Similarly, how many edges are there? There are total 6 edges for us to consider of. If it was vertices to vertices, we can see that positive or negative 120 degree from the perspective vertices, the diagonal line of these 2 vertices will not change, whereas the remaining 3 will form a group. In total 8 vertices, there are 2 which are fixed, where the remaining will form 3. In a group, there are 2 groups. How many this kind of symmetry axes are there? In total, there are 4 with 2 angles. Therefore, it contains 8 this kind of permutation. After the analysis, we will realize for this kind of vertices permutation and what we have mentioned regarding the face permutation contains certain differences. Of course, how many are there in total? Permutations is the same, of course. There are a total of 24. But the structure for each permutation, they look differently. We just take this vertex for everyone to study on the coloring problem, 2 types of colors to paint with the vertices. How many different solutions are there? Just now, or the permutation group, we have written them down one by one. And this time it is very simple that we just need to apply the polyhedron. In polyhedron, 2-order cycle is corresponding to how many? Then it is all about 2 coloring. They will be substituted into it. 2 color multiplied by the corresponding power will manage to get all the solution number. Just now it was about the coloring of the vertices. Actually, we can still perform analysis toward the face problem. For a regular hexahedron, the coloring solution for its face must be considering the permutation group of faces. Similarly, for each face, it will be labeled with number 1, 2 until 6. It also contains fixed permutations, 6 one-order cycles. cycles, corresponding to the face center to face center rotation, positive or negative 90 degree. Actually, for faces, the top and the base faces are unchanged. The vertical ones are at the height. The four faces produce a cycle. Therefore, it is the 1 square multiplied by 4 to the power of 1, which is 2 1-order cycles and 1 4-order cycles. In total, how many this kind of permutation? There are 2 different angles. There are 3 pair of face center to face center. After rotating 180 degree, we will realize all these 4s are performing pair exchanging. Hence, 2 1-order cycles and 2 2-order cycles. In total, there are 3 different permutations. Similarly, middle point of the opposing edge could be connected to be a flipping axis. We will realize that flipping over it, actually the upper face and the base face will be exchanging, where its corresponding face may also exchange with each other. Therefore, there is total 3 groups, 3 2-order cycles. For diagonal lines, positive or negative 120 degree of rotation, each 3 faces form a group. Therefore, there are 2 3-order cycles. After having a permutation of this kind, we can apply it. For example, for regular hexahedron, 6 faces are respectively colored with 2 colors. We first look at the simple 2 colors. We already have the old permutation group. We just need to apply polyhedron. For permutation of no movement, there are 6 1-order cycles, 2 colorings. Its representation is 2 to the power of 6. Corresponding to the following, there are 2 1-order cycles. There is 1 4-order cycle. In total, there are 3 cycles. Actually, corresponding to the current solution, it is 2 to the power of 3. There are a total of 6 this kind of permutations. Hence, the second item, 6 times 2 to the power of 3, so on and so forth. 3 multiplied by 2 to the power of 4, and added up with 6 multiplied by 2 to the power of 3, accumulated in the same way, and lastly divided by the number of permutation, 24. The answer is for the 2 coloring for the regular hexahedron, the solution is 10. Of course, if we looked back, originally we have mentioned that the problem which cannot be solved by Burn's-Stein lemma for the combination and the permutation on the blackboard. If we change the question into different faces, may be colored with the same color. What does it mean? It means that for regular hexahedron to perform 6 coloring, they cannot be easy to make. 2 3 change to 3, it will be sufficient. Just now, 6 1-order cycles over here, the 6 coloring, then corresponding to 2 the power of 6. Adding up with 6 multiplied by 6 to the power of 3, add up with 3 multiplied by the 6 to the power of 4. By following the same way down, then divide by 24. For now, let's look at the Burn's-Stein lemma again. It cannot solve the problem. Actually, by using polyhedron, it could be easily solved. We can look back at how dice is arranged. We all know that dice could be 1, 2, 3, and 6, maximum 6 dots on faces. Actually, it contains many varieties. So now, I'm asking that one dice with 6 faces, which are respectively 1 point, 2 point, 3, and until 6 point, then it contains different organization ways. If we allow it to rotate and turn around, how many different solutions are there? For this question, in fact, we would regard each face with different dots could be assumed as a 6 coloring on faces, so no 2 faces have the same colors. First, we may need to consider the permutation group of regular hexahedron. We use 6 coloring to make it a rotation group. We only need to consider the fixed point for cube. There are a total of 24 permutations of the faces. Within different permutations, there is only one fixed permutation, which contains fixed point. Nothing else matters. Therefore, we can directly apply Burn's-Stein lemma. It should be the number of all the fixed points divided by the number of permutations, which is a 6 factorial divided by 24 equal to 30. For other permutations, its fixed point is 0. Is it the answer for the original question? We will thinking that since the dots are different with colors, why would it so? The arrangement of the dots have a special shapes. For example, let's look at the 2 points, 3 points, and the 6 points. They are not square. It is using strip shape. Then it contains 2 different orientations. Therefore, we should not ignore it. This kind of details. Besides the computation based on Burn's-Lee lemma, we still need to consider the diversity within each coloring solution. Over here, we can see that 2 points, 3 points, and 6 points, 2 different orientation for each, where 1 point, 4 points, and 5 points, they are symmetric. There is only one orientation. Therefore, the real answer should be 30 multiplied by 2 to the power of 3 equal to 240 different type of dice structure.